In the last video, you may have heard me refer to HCl as a strong acid. So what's the difference between a strong acid and, let's say, a weak acid? Well, it's really the same definition that we used for strong electrolyte and weak electrolyte. So when we say that something is a strong acid, we say that it completely dissociates in water. And so we're going to use that full arrow. So then what is a weak acid? It doesn't completely dissociate, it partially dissociates. And we're going to use that half arrow forward and half arrow back. So look at these two pictures for the differences between them. HCl is considered a strong acid. Hydrochloric acid is a strong acid. If you see when HCl reacts with water or dissociates in water, it forms all H3O plus ions. So you can see there's absolutely no HCl together, right? There's no HCl in the solution. It has reacted 100%. But then look at hydrofluoric acid over here. Hydrofluoric acid is not a strong acid, it's a weak acid. And so when it reacts with water, it will react and it will make H3O plus and F minus, but look at it does that almost rarely. Most of the time, it is together as HF molecules. So how do I know whether an acid is a strong acid or a weak acid? Honestly, we memorize the 7 strong acids. So there's 7 of them. That's HCl, HBr, HI. Notice that these are 3 of the halogens, right? And then there is H2SO4, HNO3, that's sulfate and nitrate, 2 super common polyatomic ions. And then there's HClO3 and HClO4. So that's the hydrogen chlorate and just the chloric acid and then perchloric acid. Those are the names of them. You do not need to memorize these. This is something that if you're an AP, you will need to memorize the 7 strong acids, but for this year, for this class, you don't. And basically, once you learn that there are 7 strong, then that means every other thing that we identify as an acid must be a weak acid. These are the 2 most common weak acids. That's hydrofluoric acid, and then there is acetic acid, right? Notice that acetic acid has these 3 H's and then this 1 H. It's only that H that actually is donated, that acts as the acid and is the proton donor. If we look at these equations, again, we can see that the full arrow is used for strong acids, whereas the double-headed or equilibrium, as we will call that arrow, is used for weak acids. And then chemically, what makes a strong acid, or a weak acid? Basically, if it's a strong acid, it must mean that the attraction between these two is relatively weak, right? HCl are attracted to each other, but they will break up when they hit water. And this is also sort of strange because we would have described this as a covalent bond, and covalent bonds don't really break up in solution like ionic compounds do. But this is another exception to the rule, right? This is an exception where, they do sometimes. When we consider this not in an aqueous solution, we consider it a covalent bond, and we consider HCl a molecule. But then when it's dissolved in water, it behaves like an ionic compound. This is just another way of showing this same information about strong acids and weak acids, right? If I have this much of a strong acid, notice 100% of this breaks up into H3O plus and A minus, or reacts with water to form that H3O plus and A minus. But that means like the conjugate base there. That's what that is. But what happens if I have a weak acid? Well, almost, right? A very small percentage of it, not 100%, maybe 10%, has actually ionized, has actually done this reaction. Most of it has stayed just as the acid, undissociated, unreacted together. So now, if a strong acid completely dissociates, then if I have 1 mole of the acid, I will have 1 mole of the H3O plus. But if I have 1 mole of a weak acid, how much is going to actually react? Well, way, way less. So this question is saying to determine the H3O plus ion concentration, anytime you see these brackets, that means concentration, in an acid solution. So what is the H3O plus? Well, this is a strong acid. So that means whatever molarity this is, that's going to be the same, because HCl will 100% become H plus or H3O plus. So the H3O plus concentration would be 1.5 molar. What if I have this acid? Well, I know that is a weak acid now. So how do I know how much H3O plus will be in solution? There's a way to find out, and that's something that is covered only in AP chemistry. So right now we say, I don't know. It's not 3, it's less than 3. That's really all that we can say, less than 3 molar. This is another example of a strong acid. So again, all of it is going to dissociate, and it's going to become 2.5 molar in H3O plus. Why do I care? What is the H3O plus concentration? That's how we're going to tell whether something is, or what is the pH of that. And then this last one, look at these, which is an acid, which is a strong acid, and which is a weak acid. So I'm looking at how much they dissociate. Do they dissociate completely? And if I look here at the I minus, I see that 100% of these purple spheres, none of them have a hydrogen ion with them. So this is 100% dissociated. And so if it is 100% dissociated, this one must be a strong acid. And yeah, if I look, HI is considered a strong acid. Over here, these are nitrate ions. None of them have a hydrogen with them. That's because HNO3 is, again, a strong acid. But look over here. This is the formic acid there. And then this is the formate ion. Look at those. How many of them have 2 white hydrogens? Notice that this guy has 2. When it is unreacted, it has 2 white hydrogens. Well, yeah, most of them do, actually, right? So that means that formate, HCHO2, that formate is actually a weak acid, does not completely dissociate.